Okay, so in question one, we had a pair of cylinders that were connected, rigidly connected, so that they rotate together, with two masses hanging off of them. And we're given the moment of inertia of the two cylinders put together was 45. And in part A, part A says that we want to find M2 so that the system remains in equilibrium. And then afterwards, we'll see in parts B, C, and D, we get rid of mass 2 and then we're accelerating. But in part A, we are in equilibrium. Right, so for all the objects, we know some of the torques have to balance out to 0, and also the sum of the forces have to balance out to 0. Right, and the sum of the forces is 0 on the masses just means that we know that the tension in rope 2 is going to end up being equal to M2G, and the tension in rope 1 is going to be equal to M1G, right? Because we know that for both masses, the tension and the weight have to balance out. For the cylinder, that means we've got M1G pulling downwards over here on the left side of the small cylinder, and M2G pulling down on the right side of the large cylinder. So when we apply the sum of the torques equals 0, we get a positive torque from M1G, and that distance from the axis is R1. The torque from the second mass, or really the second tension, is negative. It's going to rotate it clockwise, and that's M2G is the strength of the force, and that's a distance R2 from the center. And of course those have to balance out to 0. The G's cancel out, and when we rearrange and solve that for the second mass, we get M2 is going to be equal to mass 1 times the ratio R1 over R2. Plugging in the numbers, you get M2 equals, well, I'll leave it as a fraction here because 20/3 of a kilogram makes perfect sense because M2 is 3 times farther away from the axis of rotation, so it needs 3 times less mass to produce the same amount of torque. So in part B and C, we get rid of mass 2, right? Mass 2 is removed, so we're just left with the cylinder having only one mass hanging off of it, right? So just one tension pulling down on the cylinder. And we're not surprised that the next question is to ask us to find, in part B, the angular acceleration of the cylinder, right? What's alpha? And we also are going to want to find the tension in the cable supporting M1, so T1, right? So now that we have acceleration, we're not in equilibrium. Now that we're out of equilibrium, we can model the cylinder as a rigid body under a net torque. So we know the sum of the torques is going to be equal to I alpha. And of course, the mass M1, we can model as a particle that's going to be accelerating, so the sum of the forces equals 0. Right, that's for the mass. So let's see. Well, that's not too hard to do now because look, if we look at a cylinder, the only thing is T1 times R1 equals I alpha, and we can just leave that as I because we're given a numerical value for it. We can solve that and we'll get alpha equals T. Well, there's only one. I'm going to drop all. We don't need to label everything with a 1 since there's only one mass left. It's going to be T times R over I. Of course, we don't know tension yet. That's being asked for in part C, and we haven't looked at the free body diagram of the mass yet, and we see that'll let us eliminate that final unknown. We know we have mg downwards, the tension upwards, and of course sum of the forces is going to equal mass times acceleration. Let's see, let's take the positive direction to be downwards here because we know we are accelerating downwards, and we know we've got a positive alpha, so that'll help. We'll say that mg is positive minus tension, which is in the negative direction, equals ma. Right, now we have our two equations. We actually have 3 unknowns if you count a, alpha, and t, but since we can always replace, since we know alpha equals a over r, right? Since a point on the edge of the small inner cylinder is going to be accelerating at the same rate as m1. Well, if we rearrange this, we can see that we will get t plus m, and now I can replace a with alpha r equals mg. Now I'll plug in for alpha what I have in my other equation, and I'll plug in this into here, and I will get t plus m times tr over I for alpha times another r, so that makes it r squared, equals mg. When I rearrange, I can solve that for t, I can factor out the t, and then if I solve it for t, what I end up with is t is going to be mg divided by 1 plus mr squared over I. And if you plug numbers into that, you should get 176.4 newtons as the tension in rope 1. Then you can go back and use this equation for alpha, tr over I, and you'll get alpha is going to be 1.96 radians per second squared. That leaves part D. Part D is just simple kinematics because you can figure out the acceleration, which is just alpha times r is 0.98 meters per second squared. You know your delta y is -1 meter. You know the initial speed is 0. So when you use final velocity squared equals initial velocity squared plus 2 times your acceleration times delta y, you should get Vf equals 1.4 meters per second. Okay.